which had a gain of 8.25. So when you divide the 1.3 volts by 8.25, you get 0.15175 volts. And then dividing that by the current sense resistor, which we know the value to be 0.01 ohms, you get 15.75 amps of peak current, which meets our spec. Okay, and our last power spec is that the motor driver will be capable of supplying no less than 10 amps DC of continuous current. So you can see we took the same measurement, but this time when the current was continuous. The reading on the scope was about 2.6 volts. The base, the zero, was already at 1.7 because that's what our op amps were at. So when you find the difference of 0.9 volts, divide that again by the gain because it was taken at the output of the op amp, and you get 0.109 volts. Divide that again by the current sense resistor, which we know the value to be 0.01 ohms. You get 10.9 amps of continuous current, and again, that means our power spec. All right, and another specification that we had was that in its resting position, the balance bot will not deviate by more than 3 degrees over a 2-minute interval. So we grabbed some data. If you wanted 2 minutes of every 10 milliseconds, it would have been a lot of data. So we just grabbed the first 15 readings, and as you can see, it was just sitting at its resting position, and it was never more than 3 degrees that it deviated.
Okay, and our economic requirement required that the robot will not cost more than $650, and as you can see from our price list, our total is $638, which is less than $650.
Okay, so now we're going to demonstrate the balance bot. So the other requirements that we haven't shown you yet are the ones in red that we're going to demonstrate. So the first one was just something we set that upon initialization, the balance bot was not expected to go automatically into its resting position, which it can though now. So that also will show. The next one says that when it's tilted to 15 degrees, it will be able to recover. So right now in its resting position, it's at, I think, 20 degrees or more either way. So we'll just start it up. And you can see that it's able to stand up and maintain the temperature.
So one of the requirements was that the balance bot will have a maximum translational velocity of at least 8 inches per second. It's not the easiest thing in the world to measure. And we actually, I'm going to turn this off for a second. We had an issue with our original motors and gearboxes. We'd spec'd out a set of motors, and that's where our current specifications came from. But there was backlash on the gears, a significant amount of backlash on the gears that we hadn't accounted for. Our original system had a 256:1 gear ratio and a 4-stage planetary gearbox. But with 10 degrees of backlash on the output, there is no way that we're going to meet any of the other specs. And just maintaining balance was really difficult. The robot was bouncing all over the place. So Monday, we actually received new motors that have been rushed in, but they've got less torque than the old motors. They're designed to run 12 or 24 volts. And these new motors just don't have as much torque available as the old ones did. So maintaining that kind of a speed, we were counting on more torque. I think we can still do it. I've got 2 10-inch marks set up. Should take about 12 seconds to run the 10 inches. So if anyone feels like timing it, I can 15 seconds from the 10 feet. And that should meet the requirement. Let's set up chairs on the 2 10-foot marks.
It's really hard when you're controlling it. One way is forward and one way is backward. So if you're positioned the other way and you hit forward, it actually will come towards you, so he's just turning it around. So, okay, it's just crossed the line now.
Not going to this to our next spec. Again, with the lower torque on the new motors, stopping is not nearly as easy as it was expected to be.
But it did put out the candle.
Yeah. We too run into walls. Actually, if you think about it to stop, you actually have to accelerate the wheels forward under the robot before you can bring it to a stop. So you're actually speeding up to stop. So you kind of have to anticipate where you're going to be. This is one of the places we wish that we could have some speed feedback or some sort of velocity feedback from the wheels position something, because without it, we don't have a good way of doing speed control or position control. All we've got is the angle. And we just got this working a couple days ago, so there wasn't really time to add extra encoders or something else. We might be able to do something with current and integrating current to figure out which way we're leaning and try and model it, but that was one thing we hadn't counted on. Let's see. That's the stopping. What's the next one?
Okay, our next one that Seven's going to demonstrate by just walking as far as he can out of the room is that the wireless transceiver must be able to communicate within a distance of at least 20 feet. So he's going to continue to control it as he walks further and further away. Still working. Still working.
We've never really tested how far we can go.
Yeah.
So we've got a pretty good range, and we simply built the receiver on our own. The transceiver is a 433 megahertz transceiver. All it does is say on or off. So we built the entire protocol ourselves. That was part of Chris's project, was figuring out how to do the communication, error checking. All this thing does is say I'm on or I'm off, and if there's other noise,